with some announcements. Of course, everybody hopefully knows that the assignment was due today. How'd that go? Yeah? Number 8 sucked, right? I knew it was going to be tough. I had to put one hard one on there for you. The rest, I hope, was pretty straightforward. I just wanted to remind people, I had a couple people who came to talk to me today that were kind of panicked about this particular assignment. Everybody gets one extension on the assignments, so you can cash that extension in whenever you want. I don't care. You get to choose. You have to notify me before the due date, so sorry, you can't use an extension on this assignment right now. It's too late. Due date's already passed. But in the future, if you find yourself crunched for time for whatever reason, I literally do not care what the reason is at all. Shoot me an email. You get an extra week on any assignment you want, period. If you're working with a partner, you both have to have an extension in order to be able to cash it in. So pay attention to that if you're working with a partner on the lab. Are there any questions about that policy? Yeah.
So you can tell you like a day in advance?
You need to tell me, the more advanced notice you give me, the better. It has to be before the due date. That's the absolute cutoff. If you come to me after the due date's already passed, like after 4 o'clock on whatever day, and you ask for an extension, the answer's going to be no. Yeah?
Just to be clear, it's an extension on like one thing, right? It's like a lab or a homework.
A lab or a homework, whatever you want. Yep. Whatever thing that you want.
Yeah.
But like I said, if you're working with a partner and you want to take an extension, then you both have to take an extension. You both have to have your extension available, right? So do with that information whatever the heck you want. Okay, speaking of homework assignments, I was this close to getting Lab 1 posted. I was so close. If I had an extra 5 to 10 minutes, Lab 1 would be on the website right now. So what that means is it's actually good news for you. Instead of having Lab 1 due a week from today, it'll probably be pushed off the due date until that following Tuesday. And I'll get the lab posted probably tonight still when I get home, or tomorrow at the very latest. I'll put a post up on Piazza whenever I get the lab posted. And we are still going to talk about the lab in class today, so I'm still going to go over some of this stuff for the lab so that when it is posted, and like I said, I was like so close. There was just a couple things I had to do. So close. I know you're all really upset as I am about that. It'll be posted soon, and we'll talk about that later today. So you are allowed to work with partners on that lab, right? So exactly one partner on that lab, right? We'll talk about all that stuff at the end of class today. Are there any questions for me about anything? Homework assignments, topics from... Oh, I thought of one more announcement, actually. The due date for Chapter 1 of the textbook is fast approaching. It's on the calendar page of the course website. I think it's, is it next Thursday? I think it might be, is the due date for Chapter 1? Yeah. The whole chapter is due at one time. I'm not going to take the time to check every single section. That takes too long for me. I'm just going to check at the end of every single chapter. So if you want to put the whole thing off and crunch the whole chapter in a day, that's your problem, right? That's not my concern. But I am going to check to make sure that you have the chapters finished on the dates that are posted on the calendar. So check the calendar page. Make sure you've got those finished before the due dates. Yeah.
And the chapter just entails doing all of the different activities.
Yep. Just doing all the activities. You don't even have to get them right. You just have to do them. And if you forget, you leave one blank or whatever, you're probably still going to get credit, right? If you leave a bunch blank, then I'm going to start taking points. Yeah.
Is there a way to see what?
I believe you can. Yeah, if you log into your Zybook and
Yeah,
It has nice little stars.
yeah, it's got little stars in the menu. Yeah, you can see what you've already done.
And the stars you can watch.
You can see what you've completed, what you haven't done. And of course, I can see all that too. That's how I grade these things. So, yes?
Yeah, just have we go to the debug so you can find us should we do anything special to that you find us. Just ensure that we register.
If you need that code that's on the website. So when you registered for the Zybook, you have to put that code in. That's what puts you in the class. If you haven't paid for the book yet, I can't see you. I can't see you until you buy the book. So if you have not bought the book, you're running out of time. You need to make that happen like soonish. Because that's due, again, I think it's due next week, next Thursday. So they're due. Any other questions that I can answer about logistics or homework stuff? Anything else? No? All right, cool. Let's do some review problems then, I guess, to start out today, and then towards the end of the day, we'll talk about the lab. So here are some review questions for you, using some Boolean Algebra, which is super fun stuff. I love talking about Boolean Algebra. Take a few minutes, talk to your neighbors, see if you can figure out how to prove these. So by proving these, what do I need? I need to start with the value that's on the left, or start with the one on the right. If you want, I don't care, either way. Apply Boolean Algebra to that expression until you get the thing that's on the right. Okay? I need to see every single step, step by step, right? Take a few minutes and then we'll talk about it. Hey, what's up? Oh, you're fine.
Yeah, you can now see logically how this has to be A or B. Yeah. Because it's A or it's not A and B. So if it's B and it's not A. Yeah, yes. I don't really think yeah, I didn't show that step, but I probably
How's it going? Who's stuck? Anybody? You people? Okay, who thinks they got it? Anybody think they got both of them? Couple? I'll give you a couple minutes longer. Let me give you a hint. You can insert terms if you need to help make things easier. So think of how you might potentially insert a couple of values to help eliminate other values. I know it seems like you might be going backwards a little bit, but sometimes you gotta go backwards to go forwards. So take another couple minutes, see if that hint helps, or maybe it made it worse. Hopefully not. What about the second one? Somebody want to come up with the second one on the board? Yeah, come on up.
the A not A?
I mean, it's all right, so one of these true.
I mean, what's the Boolean algebra? For each of these steps, you should be able to point to a property. This is not true.
I mean, I thought that if like you know, the CMO expression, if one of the conditions is true again,
Sure. I don't know that you can do that just in case property. I mean, if that were the case, can I just start drawing the terms off whenever I want?
yeah, sorry.
That's okay. That's all right. It's not a problem. There's a much simpler solution. We'll talk about it. Thanks, man. No problem. Okay. Let's talk about these. Here's the first one, right? So this is what we start with, A or A naught and B. And then this is what we have for the next step. What property did we apply to get from here to here? Can you tell me? Magic? Yeah, where did this extra value come from? What happens? Huh? Yeah, in the back. Distributed. How is it distributed? I'm sorry? Distribute to A or... So you can't distribute operations. You can actually only distribute values directly. I'm still not sure I see how that's distributed. I'm sorry?
Should you rewrite A as AA and then undistributed? So
Yeah.
It actually, it's more fun to decide what distributed for property. Where you're basically, it's like distributing and what before. That makes sense. So it'd be A plus A prime, and then A plus B. We're distributing like the A on the left.
Distributing the A on the left. Oh, I see what you're saying. No, exactly. No, I'm sorry. It was my, and you were correct in the back as well. I just misunderstood what you were saying. My bad. You are absolutely correct. You're distributing the A to this particular term, so you get A or A naught, and then A or B. Exactly. Thank you very much. That was a great explanation. I was the one who was slow on the uptake there. Okay, great. So that gets us from step 1 to step 2. Does everybody see what we did there? No? All right. Let me draw it out then. I think you would agree, right, that if I have something like this, that I can distribute across, correct? So I can say A or A, right? So consider then the alternative case where I have ors instead. Consider where I've got A or A, B. It's the same thing. The operations are flipped, right? You see how the operations are flipped? I'm going to distribute this A, but it's not multiplication, now it's addition. I can do that in Boolean algebra. That's okay. That's an okay thing for us to do. So now what we end up with is very similar to what we just saw. Not exactly the same, but very similar, where I have A or A ANDed with A or B. So I've taken this A, right, and distributed it. Since there's an AND in between these two, we see, right, we see that AND right here, right? So just like we see the OR in the middle here, and we have two AND operations after the distribution, we see the AND in the middle here, and we have two OR operations after the distribution, right? It's the same thing, just with OR instead of ANDs. That's okay. It's okay in Boolean algebra. Does that help? Help everybody make sense of that? That's a tricky one. All right. Let's go back to our proof. So we're at this step, and then we go to this step next. What's the property that we're applying to get from here to here? Complement. So A or A naught, that's guaranteed to be true, right? It either is or it isn't. It's always going to be one or the other, right? So that's guaranteed to be true. And then what's the property that we're applying here? Identity. Anything ended with true is going to be that thing, right? And we end up with our result A or B. Are we cool? Any questions about that particular truth? All right. For this second one, let's see. We have a solution up here on the board. So we can try and go through this step by step. I actually know of a simpler solution, so no offense. Thank you very much for agreeing to come up and put this on the board. But let's try and see if we can find a simpler way to make this work. Right, so I'll start with A or A, B. Right. Who can help me out here? What property should I apply first? Yeah. Okay, A is the same as A times 1. So what do I need to write? Maybe that'll be easier for me to A, B, or what? Not B. Like that? So let's see. Plus AB. Thank you. Let me just get this out of here. So that we're not confused. Okay, and so you're suggesting that we insert this term here, which is actually okay, right? What is this equivalent to? We kind of skipped a step a little bit, but I understand what you're saying. Officially, we have this step in between where we say this, right? So we could write this. 1 is equivalent to that, right? That works. This is the same property that we saw over here, right? Okay? So what next? What do we do now? I'm sorry? A and distribute it? Is that, or what are you suggesting? A, B plus not B plus AB. I just can't hear what you're saying. Take A or AB not plus AB, right? And then what's next? We've got a duplicate term here, right? So that allows us to actually eliminate one. We don't, duplicates don't matter, we can just take them out. That's okay. And then what? What do we do next? Yeah. Yeah, we factor out the A, we're left with this. And now this goes back to 1, and we're left with A. Perfect. Perfect. Questions? Yes? Say that one more time. A. A1. Oh, A in parentheses what? 1 plus B. And what property are we applying to get from here to here? I'm sorry? Distributive? So we're actually factoring it out, right? We're factoring the A out in that case? Yes, absolutely. I agree. This is how I thought of the problem. We can factor this A out. When we factor an A out of A, we get true, right? And then we're left with B. And then over here we have B or 1, which is quite clearly going to be 1. Right, so we're left with this, which then clearly is A. I like that as well. Yes. There's always going to be multiple ways of doing this. Always, always, always. Any questions? Comments? Yes. Say that one more time. A or B, B and C. could not use distribution here, right? Because in order to, so the opposite of distribution is factoring, right? So if we want to factor something out, we need to have something in common in both terms. We don't have anything in common between these terms here.
Could we distribute A and A plus B?
We could distribute, oh, we could distribute the or. I mean, is that what you were asking? Maybe I misunderstood. We could end up with this, A or B, ended with A or C. I'm running out of chalkboard space. We could end up with this. We could distribute the or, right? This is perfectly okay. Is that what you were asking? Yeah, that's all right. It's kind of hard to get in that mindset where it's okay to distribute across 4, since that's not how we learn how to do it in algebra class, right? But that's a useful technique to use. Absolutely. Any other questions, comments? Okay, who can tell me what a dual is? If I give you an expression and I say, take the dual of it, what does that mean? What do I need to do? Yeah. Okay, so we flip the operations, right? The ands and ors. What else? Yeah.
Take the complements and true or falses, but not the variables.
Right. So we only do it for the literals, right? Not the actual variables. So if I have any trues or falses, they get flipped, but the actual variables themselves remain the same. So that's called a dual, and it's important to make that distinction between a dual and what we're about to talk about in a little bit, which is De Morgan's law, which is kind of similar but not exactly the same. Right? Notice we don't touch any inversions at all. We don't touch any knots at all when we create the dual. So if I want to create duals of these expressions that we just created, right? I should be able to do that. So for this one here, I just have to flip the operation, so I end up with A and A, or A and A not, or B. Right? And then down, the result then should be A and B. Did I do that right? A and B. What did I do wrong? No, that's right. Flip the operations. We don't have any literals, right? Can I say that these are equivalent? No? What happens? A and A is always going to be false. That's absolutely correct. Right.
False or B is B.
False or B is B. It's not A and B. Absolutely right. Wait, did I do something wrong? I feel like I did something wrong, yeah. What did I do wrong?
It will be A and
Yeah, I'm
Thank you. I knew I did something wrong, and I was waiting for somebody to call me out on it, but I couldn't see what I did wrong. It would be, all right, we're doing the first one, right? So it would be A naught, and or B, right? Like this? Yeah.
and that.
And then, this part I got right. That's the easy part, right? I screwed up this part. All right, much better. Thank you very much. So now, are these actually equivalent? I think we can see a pathway to that. I knew I did something fishy. So what do? We distribute, right? I get A naught, or A B. This term we already just discussed is going to fall out because that's always going to be false, and we're left with or. Right? And for the second one, we should also be able to construct the dual. It'll be a similar process. We've got A ANDed with A or B in this particular case. And the dual of A is the easiest dual. It's just A still, right? So are these equivalent? They should be. How do we get there? Yeah.
If you distribute the A,
Okay, let's distribute the A.
and then AA is the same thing as A,
AA is the same thing as A.
and then you basically the same thing for
Yeah, and then we're up to what we just had, right? And then we can follow the same steps. Factor the A out. And then we take A and B. And then we're done. Right? Yes?
What if you do it so that it's true and false?
So I can actually have true or false inside of an expression, right? I can say A or false and that with B or something, right? So then the dual of this becomes what? B or A ANDed with 1. So I flip any 1s or 0s that I have in my expression to get the dual. You won't see literals in your equations particularly often. Usually if you see literals in your equations, it's because you use identity probably, right? Something of that sort. Usually we won't keep them around because we can usually cancel those terms out. Whenever we see literals in our expressions, we'll just cancel them out, drop them out right away. Yep. So who can explain this duality principle then? We kind of saw it in action. Who can explain it to me in a clear sentence or two? All right, do you guys not watch the videos this time? Yeah.
So you take the duals so both sides of the equation, you take both of the duals are equal to each other in the original equation.
Correct. Yeah. So if I have two equations that are equivalent, the duals of those equations are also equivalent. That's what the duality principle says, right? And that's what allows us to do things like the distribution with force in this particular case as well. That's the duality principle in action, right? That's what the duality principle does for us. In fact, all of the Boolean properties have multiple versions, one with ands and one with fors. That's the duality principle. Excellent. Any questions? Comments? Otherwise? All right, let's try some more. De Morgan's law. Oh, that's something you should memorize. You should definitely get used to doing De Morgan's law, but I want you to prove it. Start with an expression. Keep it simple, right? You could do like A or B. Not. Apply De Morgan's law, but then I want you to actually prove De Morgan's law using the Boolean algebra properties that we've been discussing.
Morgan's second to prove Morgan's first and Morgan's first.
No, you cannot.
That makes it so much easier.
You need to use the basics: identity, idempotence, distribution, etc., etc. So that's your first task. And then I want you to use Boolean algebra to prove the consensus theorem after that. And then this one's also fun. Use Boolean algebra to prove that De Morgan's law works for 3 variables, not just 2.
You use the Morgan's law to prove the Morgan's law to prove the Morgan's law.
Yes, you can. Yes, you can. Anybody get the first one? Anybody? This is Morgan. A lot of fellows put on the board. Yeah. Come on. Anybody get the second one? You all stuck on the first one? Okay. That's fine. What about the last one? Anybody work on the last one? All right. We'll take it one at a time then. Keep working, and somebody can come up with one of the other answers. Third one, you want to come up with it on the board? You can pull this down if you need more space. You can use Morgan's 2 to prove the Morgan 2. Yeah, absolutely. Absolutely. You can't use second to Morgan. Well, is that what happened?
No.
She was talking about this.
Oh, I see. Yeah. Okay. Cool. Let's talk about what we've got up on the board, and then maybe we can double back and talk about the second one. All right, De Morgan's Law. Here we see De Morgan's Law, right? It allows me to turn ors into ands, but I got to flip a bunch of stuff in order to be allowed to do that, right? That's the very technical definition of De Morgan's Law. Okay, here is a classical definition of De Morgan's, right? So we're going to start with A or B, not it. What allows me to do this? Tack a 1 on the end? What property is that? Identity? Sure, yeah. And then this is also kind of the identity property for ors, right? Inserting A or A naught into the mix. And then what happens between here and here? What are we doing? What happened? The knot got distributed to the inside. Is that okay? You guys feel good about that? No? Okay. Well, it did work. So what happened? Let's take a look at what happened after that. We distributed, right? Distributed. Well, this distribution would have actually been FOIL method, right? So we would have had a couple extra terms. I'm not sure what happened to those. Maybe just simplification. Should be A naught and A. We have A naught and A naught, which is A naught, right? A and B naught, and then A naught, B naught. So there's, at the very least, a missing A naught and B naught. Maybe another one. So close, close. Anybody have a different suggestion for me to take? Yeah, what's up? Help me out. Yeah.
Not both sides. So
At which point am I going to knock both sides? In the very beginning? Starting over again? Sure, let's do it. So we're going to knock both sides. Okay.
So you're left with just A or B equals quantity A naught, B naught,
Okay, so far so good.
then just multiply and both sides by A naught, quantity A naught, B naught.
Multiply both sides by A naught and B naught. So we say like this.
Right hand side simplifies to, so there's a dot on,
Oh yes, thank you.
and then that right hand side simplifies to false.
Yep. So that's false. So that's 0, right?
And then if you just FOIL the left hand side, it's the same.
So we need to FOIL the left hand side. So A or A, B naught. Wait, what's going on here?
A and A naught, B naught, or A naught, B naught,
A and A naught.
B naught.
B naught. Oh, thank you. I'm sorry. I was looking at this the wrong way. B A naught B naught. Like this?
Yeah, and A naught is always false, so it's not B naught.
A naught is always false, and B naught is also always false, so these don't matter. This also simplifies to 0.
So then you could get the both of the just and the both are false and the stuff that you wouldn't have to say.
That's true. Yep. So this is not quite a formal proof. A formal proof would start from here and end it here. That's what a traditional proof does, right? But let's see if we can maybe apply some things to make that happen potentially. I don't know. I have the answer on my computer. We can definitely refer to that, but I prefer to try and figure it out, right? If we can. All right. Anybody else want to take a crack at this? Or are you all too scared now? Come at me, bro. Anybody got anything for me? No? Yeah. All right, so I'm going to need you to say that again for me and give me enough time to start right now. Yep. A plus B naught, right? I'm sorry? Not? Like this? Oh, so you mean just move this over to the other side? Is that what equals to 1? I'm not sure I understand where this is going. So I'm not sure how I got from here to here. That's my... I see. I mean, I agree with you, but I'm looking for a formal step-by-step proof. How do I get from this side to this side? That's what I'm looking for. So I mean, I agree with you. I don't see how this helps me get that step-by-step proof. However. Okay. I saw a hand in the back. Does somebody have something? No? Yes? You could, or I could just show you guys the proof. Since we're running out of time here. It's on some old slides that I have, so let me just pull those up really quickly here. Let's see. They are on this set of slides right here. That's my file browser. It's Linux. Magaya. This is KDE. It's not GNOME. GNOME went way downhill lately. All right, so we got all kinds of good stuff in here. Let's see. Here we go. Here's De Morgan's. That's actually De Morgan's for multiple variables. Where's regular De Morgan's? Oh, do I not have the proof for it on here? Shoot. Well, here's number 3. Well, shoot. I'm sorry. I misled you guys on De Morgan's law. You certainly could use a truth table. You certainly could use a truth table. That's absolutely correct. Let's see. We did have this guy. I'm going to make you guys a promise right now. I am going to get the solution for this and post it on Piazza later on tonight when I post the lab. That is a promise. I will come up with an answer for you. Assured. I sincerely thought that I had it written down, and I was wrong. So I will make that right later on. For the sake of time, let's continue on to this particular guy here, which we also see up on the screen, actually, as a matter of fact. So it looks like we're going to apply De Morgan's law for 2 values first, right? Which is perfectly allowed. There's no problem with using De Morgan for 2 to prove De Morgan for more than 2. That's okay, right? It's perfectly all right. So in that sense, we see that this term is knotted, and then this and turns into an or. We can apply that one more time over here, right? To invert these, and then turn that and into an or, and then we end up with what we originally, for De Morgan's law, right? We managed to convert all of our ands to ors in the process inverting everything. De Morgan's law actually applies to any number of variables that you want. So you're not limited to 2, you're not limited to 3. You can apply De Morgan's law to as many variables as you like. Absolutely, absolutely. Okay. I'm kind of torn here because I do want to do more of these questions, but I also want to make sure I leave enough time to talk about the lab. So I think what I'm going to do is talk about the lab right now, and if we somehow manage to have time at the end, then we can come back and do more review questions. These are still great review questions. You should still take a look at them and try to work them out. I think I did post these. Did I not? Did I post these? If I didn't post these, I certainly will post these review questions, and you are more than welcome to ask about them on Piazza if you need to. All right, let's talk about Lab 1. Lab 1. All right, so I have not posted Lab 1 yet. It's coming very, very shortly. But Lab 1 is going to ask you to start using not VHDL, a very tiny bit of VHDL, but more importantly, I want to get you kind of introduced to the CAD tools that we're going to be using to design circuits in this class. So you're going to write a very, very tiny amount of VHDL. We haven't talked a lot about VHDL yet, so I'm not going to ask you to write a bunch of it. That wouldn't be fair. I'm going to ask you to write a very small amount of VHDL, and it's going to be very simple VHDL that you'll be able to figure out without too much trouble, I promise. What I am going to ask you to do is design a circuit. So you will have to design a circuit. You are going to implement that circuit and simulate that circuit on the computer using Xilinx, which is the CAD tool that we're going to be using for this particular course. So what I'd really like to do is kind of give you a tour of Xilinx and the kinds of stuff that I'm going to be asking you to do on Lab 1. It'd be nice to have this on video so that if you get stuck in the lab, you can refer back to the video and be like, oh, that's what he did in that particular case to make this work, right? And then we can talk a little bit more specifically about what I'm going to ask you to do in the lab. Okay, cool. Let me pull up. This is Xilinx. This is what you're going to see when you first start up Xilinx. Now, this program is available in all the lab computers on campus. This is also available to download. When I post the lab, I'll also post a link to where you can download this and install it on your own personal machine. For the homework assignments, you can and are more than welcome to use your personal machine. You are going to have to demo. So at some point, you're going to have to come in and demo your stuff to the TAs, right? And that probably means using the lab machines in all actuality. So just be aware that at some point, at the very end of the lab, you probably are going to have to use the computer lab machines. But up until that point, you can do everything else on your own personal machines without any problem whatsoever. And that should be true of this lab and all of the labs. So here's Xilinx, right? Xilinx does a ton of stuff. We're not going to have a chance to even scratch the surface of all the stuff that Xilinx can do in this class. I'm just going to show you kind of the basics and what you're going to need to know to work on this assignment. So in Xilinx, everything's made up of projects. So the first thing you're going to have to do when you open up Xilinx is create a new project, right? Which is the easy part. So give your project a name, demo project, right? For this particular assignment, we're actually going to be designing schematics. We're not going to be writing a lot of code. Later on, we'll be writing a lot more code. So the top level source type of this particular project is going to be a schematic. I'm going to ask you to input your circuit schematic into Xilinx. In future labs, I may ask you to write more code, in which case hardware description language is going to be your top level source. But for now, we'll stick with schematics, and I'll show you how to create schematics in Xilinx. The next page that you see here is a whole bunch of information about the FPGA. So it wants to know what FPGA you're going to be using. We're not going to be using FPGAs on this lab. We're going to start using FPGAs on the next lab. But you still have to fill these out with the proper values. These are all included. In fact, a screenshot of this very window is included on the lab report, so you can just copy all the values directly. But it's basically the model and the configuration of the circuit board that you're intending to simulate on, right? So you can just copy all of those values for now. We'll talk more about what this stuff actually means when we start talking about FPGAs for the second lab. Okay, so once you have all of those filled out, we can finish this up, and it should create a project. And this is kind of our default Xilinx view. We've got 4 different panes here that are have varied uses. Up on the top left, we have the sources view. So any code I have, any schematics I have, any files basically associated with my project are going to appear up there. Down here we have processes. So just below that we have processes. So if I want to simulate something, right, I'm going to probably kick that off from here. Or if I want to take code and dump it out to an FPGA, I'm probably going to initiate that process at this particular point, right, at this particular part of the program. Down here is the console. When you screw up, you're going to see it down here, right? That's what that is. Any errors, any warnings. And you're going to get errors and warnings. It's pretty much a guarantee. And then the big empty space is where you will eventually design your schematics and write your code. Right? Let's create a schematic. So what I'm going to do is I'm going to come up here to the project menu and select new source. And one of these options is a schematic. So demo schematic is what I'll call it. Right? And I'll go ahead and click next. And this is just a summary, which you don't have to read. Click finish. And this should pull up the schematic designer for me automatically. So here is my blank schematic. I have literally nothing in this schematic yet. Right? I'm going to ask you to design a circuit. We'll talk about exactly what circuit I'm going to ask you to design in just a little bit. But for now, I'm going to make up a little dummy circuit, right? A very simple circuit so that I can show you how to create circuits and simulate things in Xilinx. All of our gates are in this tab down here called symbols. So if I select symbols, you see a giant list of stuff. This list is huge. We are going to use maybe like 3 or 4 of those things for this lab. Just a few. And it's going to be your basic and, ors, right? Nots, XOR, maybe, right? So the ones that you're going to want to look for are things like and to. And you notice I can just type the name of what I'm looking for down in this text box here, and it filters the list. And to stands for a 2-input AND gate, right? So I can select and to from the list here, and then I can come over here and drop a 2-input AND gate in my schematic, or multiples if I need them, right? I can drop however many I want. Let me put a OR gate in there as well. Or, yeah, let's do an OR too. Let me do one of those as well. So these are really tiny. You can zoom in by holding down the control key and scrolling the mouse wheel. Right? So we can see our beautiful gates. To get out of this selection process, you see it wants me to drop more OR gates. You need to hit escape. And now I'm back to normal. So I've dropped in the gates that I need in my very simple circuit. The next thing I need to do is start wiring it up. I need to connect things. So there's a couple ways you can do that. You can go up to the Add menu and say Add a wire. Or there's actually a button right over here for adding wires, right? And then it wants you to select the inputs and outputs of these gates. So maybe I'll connect the AND to the OR, and it routes it for me. And then that might be the only wire I want right now. I think that's okay. That's fine. Well, no, let me add another one. Let me do this too. Connect those two together. Right, and then I'll add a little extra one out here for a reason that will make sense in just a little bit. In fact, I'm glad I showed you this. It may be hard to see, but that little box right there is red. That means it's angry at me right now. I need to do something to fix that. I did that on purpose, right? I knew that was going to happen, but I wanted to show you just so when this happens to you, you understand that that's a bad thing. Okay, so I've designed this very simple schematic, right? I need to explicitly add where my inputs and outputs are. Those are called ports in this CAD tool. And there's another button. You can go up to Add and say I/O marker if you want to. Or you can just select it down here on the toolbar, Add I/O marker, and then click where you want your inputs or outputs to go. It will automatically detect whether it should be an input or an output for you. So you don't have to explicitly say that. It can figure it out. So let me drop in 2 inputs and an output. These names kind of stink. So, I'd like to change them. So let me hit Escape and then double click on these. If I go down to nets, I can actually change the names to something a bit easier to type. All right, so let me just change those nets real quick. Okay, and then finally the output, will be Z. All right. So I can see I now have my 2 inputs and my outputs on my schematic. I'm going to go ahead and save. Save this, right? And I'm actually done for now. I'm done with this schematic. There's more stuff that you can do with schematics, but for the first lab, being able to do this is about all you're going to need. Right? So let me close this out. I don't actually need this anymore. And you see it takes me back to the screen that I was at the beginning. The next thing I want to do is actually simulate this circuit. I want to simulate it and see how it works. In order to do that, I need to create a test bench. Right? So the next thing I'll do is I'll add another source. I'll come up to Project and create a new source. And this time I'll come down here and I'll select VHDL Test Bench. And give it a name, Demo Test, whatever. It wants to know what this test bench should be associated with. So what am I testing in my project? In this case, I'm going to test that schematic that I just built. So that's what's selected on the list. I can go ahead and click Next and finish it up. And now this is the part where you're going to have to code a little bit, but it's going to be real easy code, I promise you. If you scroll down past all of this stuff that's at the top here, you can see a few things. Here you see those ports that we defined, right? I can see my 2 input ports, A and B, and my output port, C. So it copied those into the schematic, into the code. That's nice. I didn't have to do that, right? And now, down here, I actually have these signals, A, B, and Z. I can set those. I can actually change the values of those signals to whatever I want. I probably don't want to change the output. I probably just want to change the inputs and let the output change on its own. So down here where it says user-defined section, I'm going to come down here and I'm going to do something like this where I say A is going to be set to 0 and B is going to be set to 1, right? So what have I done? I've assigned 0 to A and I've assigned 1 to B. Notice the numbers are in single quotes, terminated by a semicolon. That's the syntax. We'll take a look at that in a lot more detail next week. Actually, we'll start taking a look at a lot more VHDL next week. For now, this is really all you need to know. If I want to test multiple configurations, which I'm going to ask you to do in the lab, actually, then I'm going to say something down here that says wait for 100 nanoseconds, right? And then I can change the values of A and B. Maybe I'll just flip them. It's actually not that short for this particular simulation, but I mean, you can make it whatever value you want, right? Okay. So I've created two tests here. There's 4 possible combinations I could have chosen. I'm just going to do 2, keep it short and sweet, right? Okay. So I'll save my test bench. And now I need to actually run it. I need to actually try this out, simulate it. Let me preface this by warning you that I had actually broke this earlier. I got it to simulate several times when I was doing this demo, and then I broke something and it stopped simulating. So if this crashes, I sincerely apologize. I did test it on the lab machines, and I verified that simulation is working just fine on the lab machines. It's just me that screwed something up. So cross your fingers. I think it's actually going to work. I'm confident. I'm optimistic. But let me show you how to run it. So up at the top here, you see we've actually got a button, one that says implementation, and one right next to it that says simulation. So the implementation view is what I want. That's what allows me to define the behavior of my circuit. So my schematic shows up under the implementation view, right? The simulation view is for testing. So the test bench is going to show up under the simulation view. When I click this simulation button, here is my test bench. This is the test bench that I just wrote. Down here in processes, you'll see Model Sim Simulator. This is what's actually going to display the results of my simulation. So to kick this off, to kick this simulation off, I just need to double click this process that says simulate behavior. And then I should hopefully see the results of my test bench. So I'm going to do that now and cross my fingers. This is where it might fail. Yep, that's not a good thing. Shoot. Well, that's okay. It's trying. We'll see what happens. I'm not super optimistic anymore. We'll see what happens. Kind of don't think it's going to work, but let's see. No. So what I would like to see here is actually a whole bunch of waveforms in the form of a timing diagram. So it broke. I was afraid of that. However, I will do this demo again on Tuesday to show you a proper timing diagram. Actually, timing diagrams is the topic for Tuesday's class, so there's a whole video about timing diagrams. We'll talk about those in a lot more detail. This is going to be the last thing that you do as part of the lab anyway, right? So you've got a lot of work to do before you get to that point. So what am I going to ask you to do on the lab? I'm going to ask you to implement a shifter. So a shifter, if I give you a binary value like this, if I shift it, that means I'm going to shift everything either to the left one position. So that's a shift to the left. Or I can shift everything to the right one position. So here's my shift to the right. Yeah, so if something gets shifted off the end, then something gets shifted off the end. I always insert a 0. Always, always, always insert a 0 to make up the difference. Every single time. This is called a logical shift. There's actually a different form of shifting that does not do that.
Arithmetic shift.
Arithmetic shift, yeah.
Well, that's only for right shift.
Yeah, but we're doing a logical shift for this particular lab. What's the effect of this shift on the number? What's the difference between this number and this number? Yeah. It's multiplied by 2, right? So if I shifted another spot over, well, it wouldn't work in this case because I've got very small numbers. But if I had more digits to work with, if I shifted it twice, it would multiply by 4, and then by 8, and then by 16. So I can do multiplication. When I shift right, then what happens? Division, the opposite, right? So that's what I'm going to ask you to implement for this particular lab. You're going to have to design the truth table for this. You're going to have to handle both directions, left and right. You're going to have to design a truth table. I think I'm going to restrict you to 3 bits just because I don't want it to be like this giant massive circuit, right? So just a 3-bit shifter. Not the most practical thing in the world, but it'll get you a good introduction to Xilinx. You have to design the truth table. You're going to have to design the circuit, implement that circuit in Xilinx, and show me a simulation that proves that it works. Right? All of that and a whole lot more information will be posted when I post the lab write-up on the website later on this evening. If you have any other questions for me, I'll stick around for a few minutes. Otherwise, have a great weekend. I'll see you on Tuesday.
So the FPGA we will use is from Xilinx.
It is, yes.
Yeah. I'm asking if I can use pointers. Yes.
If you can use what?
Pointers. It's another software. It's from Alter. It's like an ISC. Yeah,
So-
I have learned that a little bit before. I
So-
don't know if, yeah.
Everything we do is going to be VHDL, so all your code has to be in VHDL, and I'm going to ask you to submit your schematics as well. So if I can open your schematics and your code files in this program from that program, then you can use it. But if you can't, then I won't be able to grade your stuff. Because I'm going to use this to grade everything. I'm not going to install another program. I'm not going to take the time to learn another program.
Yeah, I think the demo, when we do the demo,
The TAs are going to know how to use this program, right? They're not going to know how to use that program. I'm not going to say you can't use it, but everything else in this class is going to use this program. So if I can't open your files in this program, then I can't give you a grade.
Okay.
Right?
Okay.
Yeah.
Go ahead.